Pay for evidence, not filler. By the end, you will know how to compress retrieved context into tight, traceable evidence that keeps answers accurate and cheap. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Retrieval augmented generation often returns too much text. You ask a question, and the system returns long documents. That costs tokens and blurs the signal. What we want instead is a small set of high-value sentences that answer the question and show where the claims came from. That makes downstream answers cheaper and easier to trust. RAG context compress is an extractive pattern that picks and packs the best bits of retrieved documents into a compact context. At a glance, the idea is simple. First pass finds candidate documents. Then, we split those documents into sentences. We score sentences for direct relevance to the query and keep the top ones. Optionally, we enforce a hard token budget, so the final context fits strict cost limits. This gives you a small, cited context that a language model can use to produce focused answers. We will build a tiny toy pipeline that follows that flow, so you can see each step. It uses plain Python text processing and a simple overlap score, so the ideas map directly to real systems. Now, we'll run a tiny first-pass retrieval example. This snippet quickly scores and ranks a tiny set of documents to mimic first-pass retrieval. The list D holds tuples of document ID and text, and the string Q is our query. The function T tokenizes a string into lowercase words using regular expressions. The function S computes a simple overlap score by counting how many query tokens appear in each document's text. Finally, the list H keeps the top two documents after sorting by score and a stable ID tiebreaker. The printed IDs show which documents would be sent downstream, setting the stage for later compression. Next, we'll split those documents and score their sentences individually. This example breaks documents into sentences and scores each sentence for direct relevance. The variable P accumulates tuples of sentence score, document ID, and sentence text. The comprehension inside the loop splits on periods and semicolons, then trims whitespace to get clean candidate sentences. The expression SC counts overlap between query tokens and the sentence tokens, rewarding dense matches. We then sort P by score and stable tiebreakers to pick the top two sentences into SS, which serve as a compressed context. Reducing or increasing the slice size changes how much context you keep. The printed count confirms how many sentences survive. Next, let us measure how much we actually trimmed. This snippet quantifies how much context we trimmed using a simple token count proxy. The function NT returns the number of tokens for any string, applying the same tokenizer used earlier. The variable full concatenates the full text of the retrieved documents in H, while comp concatenates only the extracted sentences in SS. We compute the ratio of comp tokens to full tokens and round to 2 decimals so changes are easy to compare. A lower ratio indicates stronger compression without necessarily losing signal. The printed ratio shows the token reduction achieved by extraction. Now we will enforce a strict token budget so the model only sees a fixed amount of evidence. This snippet enforces a hard token budget while favoring high signal sentences. The variable budget sets the maximum tokens allowed, and chosen accumulates accepted sentences. We sort the sentences in P by score and tiebreakers. Then greedily add a sentence only if it fits within the remaining budget, tracked by used. This simple policy is deterministic and cheap, yet it often captures primary facts first. Increasing the budget includes more detail and citations, but may raise costs. Decreasing it tightens the context and might clip nuance. The printed value confirms how many tokens the final compressed context consumed. Finally, we'll show how those chosen sentences can produce a short, cited answer. This example turns compressed snippets into a brief, cited answer. The variable C grabs the first document ID in chosen, mentioning cosine, and DID does the same for dot. The string ands is assembled as two short clauses that map to the query's contrast. Cosine for normalized comparisons, dot when length is informative. This is a minimal, rule-based aggregator that demonstrates the extract then answer shape without any external model. If chosen contains broader coverage, these clauses can be extended to include more nuance. The printed answer is concise and includes traceable citations, improving trust. This toy sequence maps cleanly to a practical system. Replace the overlap score with embedding similarity, and you get a scalable pipeline. Swap the greedy budgeter for a knapsack-style selector, and you can prioritize topic diversity. The core shape remains the same. Retrieve, extract, compress, answer. Recap in 3 crisp points. What it is: a compact extractive compressor for retrieved context that keeps high relevance and citations. When to use it: when token cost and answer traceability matter, like production question answering or customer support. One caveat: simple overlap scoring can miss paraphrased answers, so stronger similarity measures may be needed for fuzzy retrieval. For the next step, tune the token budget and observe how precision and answer length change. Trying a larger budget shows more citations and nuance. Shrinking it forces brevity and may expose coverage gaps. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.